Now we are going to know about the time dependent Schrodinger equation. So right now our target is time dependent Schrodinger equation. So if we consider xi, in this case xi will now be a function of your x as well as t. So new Schrodinger equation will be h square minus h square by 8 pi square m delta square xi x comma t by del x square plus u x comma t xi x comma t, and the value will be equals to minus h by 2 pi I d xi by dt, and xi is a function of x comma t. So modification is required to obtain the energy. Thus we are going to divide this particular equation into two parts. One will be your time dependent part, one will be your time independent part. So xi x comma t can be represented as xi x, just reverse the sign of the xi with two ends like this, phi t. Now it can be written as like this, h square minus h square by 8 pi square m del square this xi x phi t by del x square plus your u x comma t xi x phi x, and this will be equals to your minus h by 2 pi I d phi t by dt, and along with that you will have here xi x, which will be outside your dt. So if we remove the energy part, potential energy part, the equation comes to be like this, minus h square by 8 pi square m delta square xi x, this xi is like this, by delta x square 1 by xi x equals to minus h by 2 pi I 1 by phi t d phi t by dt, and this is considered to be as epsilon. This is valid for all values of your x and t, provided that both sides are equal to some constant, basically an energy value. So this is our time dependent Schrodinger equation. The final expression, if we try to write, it will be minus h square 8 pi square m delta square xi x by delta x square equals to epsilon xi, this is your xi like this, capital Xi x. So this is your first part. Now you have a time part also, so you can write it as d phi t, which was present there, by phi t equals to 2 pi I by h, and we have a minus here with epsilon dt. This can be finalized as ln xi t which is equals to your 2 pi I by h. We have a minus epsilon t. So xi t comes to be as your e to the power minus 2 pi I by h xi n t. So this coefficient is temperature dependent, right? So this one is your temperature dependent path. So general representation of the wave function can be like this: xi xt equals to xi x e to the power minus 2 pi I by h e your epsilon n and t. So for time dependent Schrodinger equation, this is my total wave function. Now when we get a glance of probability function for stationary state can be calculated in the same way as we have seen in the previous case. So xi star xi equals to your xi square x. This xi will carry these two halves. So from here we can write final expressions as xi x xi star x and e to the power 2 pi I, we have a negative sign, by h epsilon nt, another one e to the power plus, because complex conjugate, so 2 pi I by h epsilon nt. These two will cancel each other. Finally probability will come to be as xi x and xi star x, right? From this we will come to know how character of wave function will change with time, that is between the transitions. Thus we have already seen the time dependent part and the time independent part. So when we have already seen these two, we have already known that the combination of L and M states comes to be as your xi equals to Al xi L and plus Am xi m. Since for particles in a box of xi L and xi m is a stationary state, xi L and xi m when equal, it is always possible, but in general case it may not be stationary. Thus xi L and xi m is taken as different states. For conversion of L to M, what we are going to see is that this one, when we consider for conversion of L to M, your Al value when equals to 1, your Am value equals to 0 at initial state. For this one, this wave function, Am xi m plus Al xi L. Similarly, when you have Al equal to 0, Am equals to 1, which is a final state. So whether transition will occur from one state to another, if it takes place, then what is the condition? So that we are going to finally see. So on applying electromagnetic radiation, we have a general equation: H naught is equals with your xi will be equals to your epsilon xi. So Hamiltonian H naught is the before the interaction with the electromagnetic radiation. So now you are applying electromagnetic radiation, potential will get changed. The change of the Hamiltonian due to interaction of electric field with electromagnetic radiation. So new Hamiltonian will be H dash. So total Hamiltonian when we consider will be equals to your H naught plus H dash. So for this case you can write H naught plus H dash in brackets, and you have xi m with a Am plus xi L with a Al. This comes to be equals to as minus h by 2 pi I d by dt, same function al xi l plus am xi m. Now if we operate it is like this, al h naught will be applied on the wave function only, plus al h dash xi l plus am h naught xi m plus am h dash xi m. This comes to be equal as minus h by 2 pi I xi l dal by dt minus, this is my time dependent function, so it is under the dt function, h by 2 pi I al d xi l by dt. Similarly, you have more expressions. Let's go to the next page. In the right hand side you have h by 2 pi I am d xi m dt minus h by 2 pi I xi m dam by dt. Now which get cancelled? Of terms which can be neglected, which do not involve any perturbation, will be equal to 0. For example, these terms will get 0. This one, and we have this one. Similarly, another one will be this one, and in the next page we have this one, that is your d xi m dt. So we are going to now multiply both sides with your xi m star and integrate it all over the space. And finally, after complex calculations, we are going to get equation where final transition of particles by electromagnetic radiations can be obtained. We are not going to deal with the derivation in details. If you want to see the derivation, you can see it. I will give the link of the picture in the description box. So in this case, for transition, dam by dt is not equal to 0, and your integration minus infinity to plus infinity, we are going to get xi m star h dash xi l dx not equal to 0, and this is known as your transition moment integral. Transition moment integral. Now, molecule, if has a dipole moment, will interact with different kinds of radiations to provide energy, and h dash which we had considered previously can be given an expression with regards to your dipole moment also. So in this case, we have h dash to be equal to as your mu x e x, or you can write it as mu x your ex. Molecule, always inside the molecule there should be change and there should be a charge separation in order to interact with your electromagnetic radiations. Similarly, criteria of spectroscopic selection rule, when we consider, always remember that if system does not have any kind of dipole moment or radiation, induced dipole moment, no kind of spectroscopy is going to occur. Similarly, symmetry of wave function, if xi m and xi l do not follow each other's symmetry rule, transition will not occur. So two rules which we have now derived is that this dipole moment should be having some value, and second is that xi m and xi l has their symmetry criteria. So probability of having different combinations are present. We need to have three symmetry elements involved. One is symmetry of initial state. We need to consider symmetry of initial state. Another one we need to consider is symmetry of dipole moment. And the last thing which we need to consider is symmetry of final state. These three symmetry criteria are being involved in case of spectroscopy. So, symmetry in particle in box, we have already seen the waves, and from there only we can understand there is some kind of symmetry. Nature of symmetry of dipole moment, suppose when we are considering value of mu, that is this one, to be as your opposite to the value of as it is minus y, which is opposite to the value of another mu which is plus y. So, it is antisymmetric. When we consider this wave, in this case only you can see here n equals to symmetric, whereas in this case the wave is equals to antisymmetric. Again, for the third case, if you consider this is symmetric and this is antisymmetric. So, if wave function is multiplied of 1 is multiplied with the wave function of 2, that is one symmetric is being multiplied by the wave function of antisymmetric, then your value comes to be as antisymmetric. So, what are the ways of multiplication? Let's see. So, when we multiply symmetric with symmetric, the probable wave function will be symmetric. Similarly, when we multiply any one symmetric with antisymmetric, we are going to get antisymmetric. And the last one is if we multiply antisymmetric with antisymmetric, we are going to get symmetric. So, for a transition to occur, xi star, xi L should be antisymmetric for transition. That is, one should be symmetric symmetric or one should be antisymmetric antisymmetric. Difference in symmetry is not acceptable. So, this must be symmetric. For that, plus and minus transition is accepted, plus transition is not accepted, and your minus transition is also not accepted. These are not accepted. So, finally we have come across where the rules of selection for case of spectroscopy can be obtained. For a transition to occur, electromagnetic radiation induces transition. So, a transition is always proportional to your integration of plus infinity to minus infinity xi L star your mu x xi m. So, this is your final wave function, this one is your dipole moment, and this one is your initial wave function. So, for a particle in box, if we consider for particle in box, in that case this has become equals to integration a by 2 and minus a by 2 xi L star xi m, and in between we have mu x. Allowed transition will be from plus to minus only. N for your emission purpose, n can be from 1 to your 2, 4, 6. This is for emission. Whereas for absorption, if we consider, we have n equal to 2, 4, 6 to your 1. This is the selection rule. Transition depends upon the symmetry of the wave function. Peak intensity we are going to derive in different cases, and we are going to see in details in different spectroscopy. So, what are the rules which we have already obtained? Here we are going to observe electronic transition. Weak transition and strong transitions generally depends on selection rule, where if the transition moment integral has a high value, there is a strong intensity. Magnitude of xi will increase as well as your magnitude of dipole moment will increase. Population of two states within which transition is combined or considered, that is also important for a occurrence of your particular intensity in a spectroscopy. So your population is equals to your or proportional to your e to the power minus E is your energy by RT. E is the energy which we want to get in the population. This is Boltzmann distribution. Low temperature, most population in the ground level, and with increase in the temperature we are going to see population going at a higher energy level. So as energy level is increasing, the population increases with temperature. So if population is less, signal is not much intense. So electronic spectroscopy is not much affected by temperature of the system. In contrast, when we will talk about rotational and vibrational spectroscopy, we are going to see the effect of temperature. So this particular introduction and origin has been distributed in 2 videos. Hope this was helpful. Thank you for watching. Do not forget to like, share, subscribe and comment.